Good morning, everybody. It is my great pleasure to welcome my colleague from the University of Oslo, Professor Nadia Larsen. And she is a very prominent figure in the area of operator algebras. In particular, she works on semi-group sister algebras, equilibrium states, high-rank graphs, Hecke algebras, and she also has experience linking theoretical mathematics, theoretical stuff, to application in signal processing like wavelet theory and mathematical physics. When it comes to her academic contributions, she played a significant role in the Abel Symposium conference proceedings, and she had a section titled Operator Algebras and Applications. She contributed significant research on equilibrium states, including a notable paper titled KMS States on Mika-Teplitz sister algebras. And she is on the editorial board on the Journal of the London Mathematical Society and the Bulletin of the London Mathematical Society. And I would strongly recommend her as an editor because when we have a paper which we want to publish there, we send it to Nadia, and she is a very good editor. She handles referees and everything very well. So I strongly recommend her as a person to whom send papers. And yeah, let me add one more personal detail. Nadia is originally from Romania, but she's been in Oslo like for decades, I suppose. So, Oslo and Norway is a very charming place. So without any further ado, let me pass you the floor. The floor is all yours. Take it away.
Thank you, Piotr, for this introduction. So I guess I have the screen from my side here. So yes. Do you hear me well?
Yeah, we hear you well.
Okay, very good. So thank you for your introduction, and thank you for the invitation to give a talk at this event. So I understand that it's an on-site and online hybrid event, and with a variety of talks. So what I will talk about has titled Spectral Triples for Inductive Limits with applications to noncommutative solenoids. But I would rather say this is this is joint work with my colleagues Carla Farsi at Boulder, Therese Landry in California, and Judith Packer at Boulder. So the talk will be more about noncommutative solenoids, and because we want to construct and understand spectral triples for them, there will be a view to this construction via inductive limits, but really inductive limits of spectral triples will play a smaller role in the talk, and they will appear towards the last part of the talk. So noncommutative geometry, it's a vast field, and I understand that you've already been exposed to introductory talks and already probably have some experience listening to topics in noncommutative geometry. This is a vast program. It was pioneered by Alan Kohn in the 1980s. So roughly, as you may have heard, the aim of the program is to, well, for reasons coming from various areas of mathematics and physics, is to try to extend and understand notions of topology and Riemannian geometry, but moving them from the ordinary points and algebras of commutative functions to algebras that are typically non-commutative. And almost hand in hand, alongside this program, Mark Riefel proposed a theory of non-commutative or quantum metric structures on algebras that are possibly and often indeed non-commutative. Although there is, just even for the commutative algebras arising as group sister algebras of abelian groups, there is much to learn about this non-commutative structure. And there's, along the development in this field, there's been a rich interplay of some of the key concepts. One of the key concepts in non-commutative geometry is that of a spectral triple. This somehow leads to a generalization of geodesic distance on some sort of non-commutative manifolds. And in quantum metric structure, a Lipschitz seminorm is the notion that leads to this new structure that can bring new examples and new insights. So some primordial examples of spectral triples appear already in a paper by Kohn in the late 1980s. Kohn introduced unbounded Fresnel modules and on a with a particular additional property, then actually a very natural one, those unbounded Fredholm modules are so-called spectral triples. One of the major motivation is the example of the algebra of continuous functions on a compact spin Riemannian manifold, for which there is a natural action on an L2 space of so-called spinors, and there's a natural Dirac operator rising from the spin. And then Kohn showed that one can view the distance between 2 points x and y on the manifold as a classical distance, but in this non-commutative version from the triple, from the Dirac operator, it can be recovered simply as a majorization of values of functions or elements in the algebra at the points for which the measure, somehow the distance of f to the Dirac in norm, and this of the commutator in norm is at most 1. And thinking of continuous functions on the torus as a group Sistra algebra, there is a natural word length function. One can pick a set of generators, and then the group Sistra algebra of Z acts on L2 of Z in the regular representation, and there's a natural operator that will act as a Dirac operator. D implements an action on L2 of Z by acting on a G with multiplication with the length of the element G. And this length function, as G increases, goes to infinity. So this has the properties of, so those two are examples of spectral triples. C of M with its faithful realization on the Hilbert space H and the D, and sister of Z with its realization L2 of Z and the Dirac operator.
Nadia, may I cut in for a second and make a comment about your first point? So it's very interesting because, of course, we have this primordial example of a spectral triple. We just take smooth functions on a closed Riemannian spin manifold. But it's been decades and it's been extremely tough. Alain was saying that it was one of his hardest theorems he proved. To have a so-called reconstruction theorem, in the spirit of Gelf and Naimark. Of course, every function algebra on a compact Hausdorff space is a commutative sister algebra, but to prove the other way around, that every commutative sister algebra is a function algebra, that's quite an effort. So we have a similar theorem here. If you take a commutative spectral triple with a bunch of axioms I wouldn't even dare to explain right now, not that I remember them, you can actually prove that it must be smooth functions on a manifold. And I believe the biggest obstacle was to show that it's really a manifold, not an orbifold, right? Am I correct?
Okay, so removing, I don't know the details, but yeah, so removing any possible singularities, you really want the smooth structure, right? Okay.
But it's amazing that you can encode smooth manifold in a purely operator algebraic structure. I find it absolutely amazing.
Well, that's one of the reasons noncommutative geometry is one of our main interests.
Precisely.
So let me just give a formal definition now of a spectral triple in a form that I hope is not too different from what you have seen. I mean, essentially, this is a slight variation of the version of an unbounded Fredholm module. So a spectral triple consists of a unital Sistra algebra, a unital faithful representation. So the faithfulness makes it spectral triple rather than just an unbounded Fredholm module. So A acts on a Hilbert space faithfully. There's a self-adjoint operator D acting in H, so not necessarily bounded. And we're asking that this D has compact resolvent. So resolvent, it's defined as the inverse of D minus lambda times the identity whenever lambda is not in the spectrum of D. And we're also asking that there's a dense star subalgebra, curly A, regarded as a smooth subalgebra, because on this subalgebra, we can sort of do those commutators. This is sort of the derivation type of thing where the Dirac operator with its commutator with pi of A should extend to a bounded operator. I mean, it's densely defined and should extend to an operator in B of H. And this algebra, curly A, should be, it becomes norm dense. So this is a formal definition. So we're looking for essentially 3 ingredients: an algebra, a representation of it on a Hilbert space, and an operator. And we like to recognize inside it also a dense star subalgebra. So this definition came in the 80s. there have been many example classes, and I will just, without, I have make no claim of being exhausting all the examples that have been constructed, but just I'll concentrate on some that somehow incorporate the elements that I'm interested in for my talk. So one of them is the work of Riefel, who extended the structure of a spectral triple from Z to an arbitrary Z to the D. A lot of work goes into this. Once again, one can pick a length function for a set of generators. You can pick a nice set of generators. And you let your group algebra act on the L2 space, little L2 space, by the regular representation. And again, the operator D is multiplication with the length of G whenever you act on an L2 element. And adding a twist to the case where these two produces a Sistra algebra that is then realized as the so-called rotation algebra that we will hear more about. So Riefel also constructed, in fact, his construction here in the first point, it's also in the case that there is a twist or a two co-cycle. And then so he obtained spectral triples for the rotation algebra A theta. In quite a different direction, but also very important, there's been work by Christina Antonescu and Eric Christensen, who constructed, among other things, one of their construction was of spectral triples for AF algebras. And AF algebras are inductive limits. So we're seeing here already a twist on a Sistra algebra of a group, of a discrete group, and an inductive limit. And this will be the main sort of application that we will look at. So let's just see what the rotation algebra is. So the rotation algebra is defined through a parameter theta, a real parameter. Let's just pick parameter in 0, 1. The noncommutative 2 torus of angle theta, or the rotation algebra theta, is the universal Sistra algebra A theta, generated by two unitaries, a U and a V, subject to the commutation relation that the product UV differs by, it's equal to the product VU times this phase factor, the exponential of 2 pi I theta. So theta can be rational or irrational. And especially the irrational case has attracted a lot of attraction or a lot of interest. And it is known that A theta is also expressed as an inductive limit of Sistra algebras, each of which is a copy of the group algebra of Z2. So it's an inductive limit of those commutative Sistra algebras. Now, in the early 2010, 2013, Frederick Latremoulier and Judy Packer proposed the construction of a non-commutative solenoid, which has one definition or one construction as an inductive limit of rotation algebras. So the non-commutative solenoid is curly A theta S is a limit of rotation algebras A theta K, where one chooses the sequence of parameters theta K in a careful manner so that one can construct this limit. One needs compatible maps from one A theta to the next A theta. So we have here two Sistra algebras, the rotation algebra, and then a limit of rotation algebras, each of which is an inductive limit. And we would like to understand how one can obtain spectral triples for the noncommutative solenoid, possibly from the rotation algebras or possibly in some other manner. First, we're going to view this as twisted group Sistra algebras.
Excuse me, may I have a question?
Yes.
Somehow I don't understand this known fact that A theta is an inductive limit of something which is commutative. So copies of a commutative Sistra algebra C star Z2. So how it is possible that if you take an inductive limit of something which is commutative, and in fact those are the same algebras, you get A theta? I don't get it.
Well, yeah, I think you have to, yeah, encode this in the twist or encode it in the maps. It's not a very trivial construction. Yeah, I hope I'm having it correctly, but I will have to think about. Maybe I've not presented it the correct way.
So somehow this theta is encoded in the connective.
Yes, it's certainly not. Yeah, it's not a very canonical. But
Okay,
it can
thank
be
you.
built essentially from, or if you want, it's a circle algebra. It's a limit of circle algebras. That's one way to see it. Okay, let me move on with the solenoids, and this is where we actually want to see what happens. So the twisted group algebra picture of the rotation algebra and of the noncommutative solenoid arises from looking at the discrete group gamma and a map defined on gamma times gamma with values in the circle, satisfying a certain property that essentially allows us to treat representations, projective unitary representations of gamma. So the map sigma satisfies a commutation or a sort of co-cycle property. So a sigma st comma r is the sigma of s comma tr sigma tr. And we're also asking that the sigma is normalized so as to take value 1 on the identity pair E comma E in the group gamma. We're going to call this a multiplier on gamma. And for the data of a discrete group gamma with a multiplier, we take the L1 functions on the gamma, just the L1 space on gamma, and we define the twisted L1 gamma sigma by endowing the L1 gamma with a convolution that is twisted by the sigma. So for functions f and h in L1, the twisted convolution sends a group element S into the sum of f of t. Essentially, it's the usual convolution f of t, h of t inverse S, but we're multiplying each term with the sigma of t inverse S. And the same thing happens with the involution. We send the S to the conjugate of f of S inverse, but we also multiply the sigma at the value S inverse and conjugate for functions f and h in L1. And now we use the same convolution formula to define a left sigma regular representation of this convolution L1 sigma gamma sigma on the L2 space, L2 gamma, just the regular L2 gamma. So the lambda acts on f on a vector psi simply by just taking the convolution of f with psi. And once we have this representation, we take the image inside the bounded operators on L2 of gamma and call that the twisted group Sistra algebra of gamma with the twist sigma. So this is the structure of the twisted group Sistra algebra. So let's look at
Sorry,
an
may I have a
example.
question?
Sorry?
May I have a question?
Yes?
So I presume that there is also a universal variant of this construction. Am I right?
Yes.
Okay.
Yes, and for the cases we are that of interest, so for the cases where gamma is amenable, the universal and the reduced will be the same. And of course, the functions of compact support of gamma with the same twisted convolution, they sit densely inside L1 gamma sigma, and therefore inside the reduced group Sistra algebra of gamma sigma. Yes, but we will concentrate on the reduced one with this representation because everything has to act for our purposes on a Hilbert space. And because the groups we'll look at will be amenable, so there will not be a difference. So the rotation algebra arises by considering the multiplier sigma, which to a pair of integers z1, z2, y1, y2, produces the number e to the pi theta z1 y2 minus z2 y1. This is a multiplier, and then one shows that the theta is the twisted group Sistra algebra of the group Z2 with this multiplier. So now if we want to form, to see how this noncommutative solenoid arises as as a group cis-true algebra twisted by a co-cycle. First, maybe we have a look at what the solenoid is. So the classical solenoid is a nice compact space. So it's really a topological group. So it's a group that's identified as an inverse limit of compact spaces or compact groups with some connecting maps that essentially all take an element and raise it to some fixed power. So let's look at an example. So if we fix a prime P, we look at the subgroup of rational Z1 over P, where all elements are fractions of some integer modulo a positive power of the prime P. So this is the subgroup. One can realize this as an inductive limit. So if you think of the group Z, you produce a limit of Z by multiplying any integer k with P. So you produce higher and higher powers of P at every level as you move along the limit. So as you move along this inductive system, so this is an inductive system of groups with connecting maps. And in the limit, we've produced enough powers of P, multiples of P, so that we can identify with the subgroup of Q. Now, Pontryagin duality tells us that the dual of Z is the torus. The dual of multiplication by P on Z will become raising the power to the power P on the torus. So taking the Pontryagin dual of each copy of Z through the functoriality of the limit will give us a limit, an inverse system of spaces. So the maps now go the other way. So there should be some dots here somewhere. So this map transforms into the map T maps onto T, raising an element Z to the power Z to the P. And this limit is the so-called P solenoid. So we can think of it as all the tuples of elements on the torus, countable tuples, so that the n plus first element's pth power is the previous element in the sequence Zn. So this becomes a compact group when we endow it with a topology from T to the n. And now we'll try to use
Very good.
this
Sorry,
element.
there's a question. Go ahead, Adam.
Sorry?
I presume that this limit of this tori is the topological inverse limit. And I have a quite general question, since you have two inductive limit and you apply Pontryagin duality. So those systems are realized in the category of locally compact groups or something more? How you view this inductive and inverse system? You apply Pontryagin duality functor, and this turns this inductive system to the inverse system, yes? But this inductive and inverse systems are both in the category of locally compact groups. Am I right?
I think yes, that's yeah.
Okay, thank you.
Yes.
And this topology is the usual Tikhonov topology on Tn, right?
Yes, the product topology on Tn, yes. Yes. So to define a noncommutative geometry or a noncommutative version of the solenoid, Latte-Mollier and Packer first, so one of the versions of the construction is to produce a multiplier, sigma theta, on a group gamma that picks up the direct product of those subgroups of Z, Z1 of Q, Z1 over P times Z1 over P. So Z2 will be replaced by those two groups. And in defining the multiplier, so if I define a multiplier for a theta here through this formula, so now if we replace Z2 with Z1 over P and Z1 over P, we still want to produce a complex number and see what that gives us. So we need to choose a theta, but now somehow we want to incorporate this structure of the solenoid. So the theta will be a parameter that in principle, you can think of it as coming from the solenoid. So the theta is an is a sequence, is an infinite sequence of elements in 0, 1 mod Z, such that, so now I'm sort of reversing the realization is so that the pth multiple of theta n is the previous theta n minus 1 in the sequence. So you sort of work modulo Z. So we replace the theta n 0, 1 with a sequence of thetas, and the noncommutative solenoid as defined by Latomolier and Packer, A theta upper S, S from the solenoid, and P from the prime, it's the group algebra of this gamma twisted by the multiplier sigma theta that does the following. The sigma theta on a pair of elements from gamma. So now this multiplier acts on gamma times gamma. So we would have a tuple of elements in gamma. This is the first one, and another tuple of elements in gamma. And we have to produce a complex number on the torus. And this will be e to the 2 pi I theta of the and of the order K1 plus K4. So again, the first and the fourth are meeting, plus, and then we record the A1 and A4. So anyway, so one can show that this definition of a map sigma tau on gamma times gamma has the properties of a multiplier. So there is indeed a reduced Sistro algebra. I missed a little r here, but as I said, those groups will become amenable. So it's really the reduced group Sistro algebra we are interested in. So this
Sorry,
is
can you remind me what SP is?
Sorry, what S?
SP. It's probably on the previous slide.
I think it's this one,
Okay,
yes. And
okay.
I sometimes I see that because it depends on this choice of P, and you can choose any P, right? And I think I have at least in one place I missed. I mean, I'm not putting it up here because it will become too heavy. But it's so essentially you need a parameter for every. Yeah.
So here you could skip S and just write P.
Yes, that's another way. Yes, but it somehow depends on it's the solenoid.
Oh yes,
Okay.
S for solenoid, yeah.
So let's see, how do we view those as inductive limits? So once again,
one more question.
Yes.
Probably stupid one, but
No.
let me ask it. The solenoid as a topological space, what is the dimension of this space? Since it is realized as a subset of this huge product, but there is a condition on each coordinate. So is it one-dimensional?
I think, yeah. Well, it may be even, so it's a compact space, right? Yes. So yes, I mean, as I said, it's very, maybe I'm just putting it there so that it gives us an indication of what the classical space is. But in general, we are also very interested in zero-dimensional spaces. But I'm really trying to illustrate the idea of this of the Sistro algebra associated to a choice of parameters. So it's not, the Sistro algebra will not directly be a deformation of the solenoid. So, okay, so let me fix this set of parameters, omega p, we call it now omega p. So I'm just, because I'm really just recording the thetas in this form, in this discrete form. And we realize this twisted algebra for the solenoid in the following manner. So for the sequence of parameters theta, so I'm not really giving all the details here, but the details are very, very involved. But what matters here is the even parameters in the sequence. So the theta 0, the theta 2, theta 4, generally theta 2n plus 1, and there are natural connecting maps between those a thetas. So this will be the rotation algebra, and there's a natural connecting map on this. There is some computation to do. And okay, so let's see how would we see just the idea of why we would get rotation algebras anywhere. So remember that the gamma is defined as this Z1 over P. So those are all the rationals with any positive power of P. So if we fix an N, and if we fix the subgroup of this gamma, where in the first component and the second component, all the powers are P to the N, call this gamma N, restrict your multiplier to this subgroup. In this subgroup, gamma N, look at the generators, 1 over P to the N, comma 0, and 0, 1 over P to the N. When we regard those elements inside the noncommutative solenoid that we define as a twisted group algebra, if one looks at what those are, one really sees that only the even indices appear. And if one does the product of those generators, and through what the maps are doing, one really discovers the relations in the rotation algebra with this angle theta to n. So with the computation in place, one sees that this multiplier that we defined on the entire product here times itself, when we restrict it to only keeping powers of P to the N, we obtain a canonical, through the universal property of A theta, we obtain an isomorphism with A theta to N. And this is naturally then identified with the twisted algebra of Z2 with the parameter that simply just picks up the theta to N. So none of this is immediate. One has to do the computation. But the non-commutative solenoid is an inductive limit of those of this type of sequence of rotation algebras. All right, so we keep in mind that there is this sequence, this inductive limit over the even indices. So I will have some examples at some point. So actually right here. So there is work by Aiello, Guido, Isola in a series of papers where they studied spectral triples on so-called periodic non-commutative solenoids. And they obtained semi-finite spectral triples. So here, if you choose P to be 2, and you choose your infinite sequence theta to be 2/3, 1/3, 2/3, 1/3, so you choose it periodically, then one can show, using the properties, that the non-commutative solenoid associated with this theta, so it picks just the even indices, right? So it becomes a limit of the rotation algebra with the with theta, all thetas equal to 2/3. So in particular, this is not going to be a simple algebra. And Aiello, Guido, Isola, they construct semi-finite spectral triples on this class of examples. For an example of a non-periodic and a rational case, pick any prime P and pick any A and Q integers that are coprime. Then we can get a non-commutative solenoid by the following choice of thetas. So theta 0 is just A over Q. Theta 1 divides this by P over Q. Theta 2 divides by P squared, and so on. So theta 2 to the n is A over P to the 2 to the n Q. And this sequence fulfills the compatibility requirements for being in omega P. So, and produces an example of a non-commutative solenoid for a non-periodic sequence. So in their work, Letremolier and Packer showed that the non-commutative solenoids have a structure of quantum compact metric spaces in Riffel's sense, but also in Letremolier's sense, there is a certain generalization of the Gromov-Hausdorff distance called the propinquity And they can also be realized as limits in this type of generalized distance of the non-commutative tori. And work of Arausta and Franz Luev, where the main motivation is to study Gabor analysis, they do produce a characterization, they offer a characterization of a certain type of spectral triple of some non-commutative solenoid of a particular sort. And as I said, Aiello, Guido, and Isola produced a series of papers in which they find that they construct semi-finite spectral triples for periodic non-commutative solenoids through quite a different construction. So somehow our question and our aim here is to understand whether non-commutative solenoids of the most general case, of the most general sort, admit spectral triples. And for the spectral triples, it's interesting to know whether a certain type of operator associated to the spectral triple is of trace class, in which case we call them finally summable. So those are the questions we're trying to answer. And an additional question would be, what is the quantum compact metric space structure from those spectral triples? Is there such a one? So are they compact quantum metric spaces? So we're going to answer first this using the twisted group algebra picture, and then we will look at the inductive limit. So a length function on the discrete group is a map from gamma to the positive line where we only have value 0 at the identity element, and the L is involutive, and L satisfies this triangle inequality. This is semi-multiplicative, so L of gamma 1, gamma 2 is less than or equal to the sum, so it's sort of sub-additive. Once one has a length function on a group, there's a natural way to define the Dirac operator. Now I'll call it D sub L on the continuous functions on gamma, or on the continuous function on gamma with a twist from a multiplier sigma, if there is one. So again, the operator just acts on the function by multiplying with the value of the length function on the element gamma. So then the algebra, the group algebra, this should be a reduced group Sistra algebra. The reduced group Sistra algebra, because we're not assuming gamma amenable. So this would be a reduced group Sistra algebra of gamma with a twist from a multiplier sigma, represented on L2 of gamma, and this operator will be a spectral triple whenever L is proper, in the sense that any ball of finite radius is finite. So the inverse image of any finite interval here is finite. And we also want the range to be unbounded and be discrete. So when this happens, then
question.
Right, yeah.
Just a sanity check. So I presume that this condition of L being proper corresponds to compactness of commutators, and this unbounded discrete range corresponds to having compact resolvent. Am I right?
Yes, yes.
Okay, thank you.
Yeah. So, yeah, so the length function being proper, I'm just writing the definition here, just means that every ball of finite radius has to be finite. And it turns out, for most of the interesting properties that we're hoping to get for the spectral triple, such as finite summability, but also relations to the compact quantum metric structure, we need something more. And this condition of bounded doubling, I didn't write it here, but this was introduced by Michael Christ and Mark Riffel. And what it says is that the size of balls of a ball of finite radius where we double the radius is no larger than the size of the ball of radius r times some constant that only depends on the length function L. So this notion, due to Christ and Riffel, generalizes polynomial growth. If the group is finally generated, then bounded doubling is the same as polynomial growth. And this is essentially what is needed to obtain a compact quantum metric structure on the group algebra of gamma, or of the twisted group algebra. But the group we have here is not finally generated. So in a sense, we're looking at an example where finite generation is not present, but still this property of bounded doubling is very important. So we are interested in finding a proper length function on our gamma, which is the product of z1 over p times 1 over p, with those nice properties. And indeed, we can show that, first of all, for fixing a prime p, and just looking at z1 over p, the choice that produces, so there is a choice of a length function giving both properness and bounded doubling. So this is also proper. The choice is that one chooses the sum of the Euclidean distance and the p-adic distance. So the p-adic norm, if you take your r and you try and pick out of the r, you write it, you pick out the highest possible power of p that you can get, then p to the minus n would be the p-adic norm. So in a sense, we have a diagonal embedding of z1 over p, both in r and in qp, the p-adic numbers. And we need both of them in the length function. And once we have this, the constant it's there, so one can compute it. And of course, it's then natural to take a direct product, and the function that just sums up this LP on the first component with the LP on the second component becomes a length function with the nice properties that we want, bounded doubling.
Sorry, could you quickly give some reason why this exponent is equal to 8 in this constant? Why 4 times p to the 8?
I would have to go very to the there's certain squares are coming, there's certain estimates. I don't have the argument in my head for
Okay.
why this works, but it's through the bounded doubling. Certain squares appear in the estimates once we start counting number of elements.
Okay, thank you.
Okay. So then we can show that for a prime p and the group gamma given by the direct product of z1 over p with itself and a parameter theta, which is in the sequence of theta pn equal pn minus 1 mod z, and the group algebra, again, the reduced or the full, it's the same here, with the left regular representation on H equal to the L2 of the gamma, and the Dirac operator dp given as the operator given by pointwise multiplication by this L function that just adds up the components from this from the first and the second coordinate. This one becomes a spectral triple for this noncommutative solenoid. And the smooth subalgebra, the one where the commutators with the Dirac extend to bounded operators, it's just the continuous functions with compact support on gamma with this twisted multiplier. And the finite summability follows from the bounded doubling and the additional properties, the properties of the length function. So whenever t is a parameter that is larger than the logarithm of this constant that we obtained from the doubling, we have the finite summability, so the identity plus the square of the Dirac raised to the power minus t over 2 is the trace class operator. So essentially one has to isolate, one has to understand the list of eigenvalues here, and you sort of split up your according to some, you sort of zoom out according to some telescoping. It's a telescoping type argument that has been used in other contexts to show that this is trace class. Okay, so this produces a spectral triple. So how do we get to the inductive limit? Well, recall that we have this inductive limit of the noncommutative solenoid as a limit of rotation algebras. And since we know that we have rotation algebras along the way, we could also say, well, can we start the other way? Well, it's not so obvious that one can just put together inductive, if one has a spectral triple on each component, it's not obvious that you can put them into a limit and get the spectral triple. It has been constructed, so the AF algebras and the spectral triples that Antonescu and Christensen constructed are construct it on an inductive limit, but it's not so obvious.
I mean,
So let me
don't you
just
have in general
recall.
a problem that if you have, say, a map between some star homomorphism between sister algebras whose appropriate dense subalgebras give you spectral triples, that is not clear at all how to induce one spectral triple from the other?
Well, you will see in a moment. It
Okay.
is clear. It is clear how to make a natural choice, an informed choice. The problem is how do you prove the properties? So that's why I'm just repeating this slide of a spectral triple. So a spectral triple has those three components, AHD, with the additional information of the smooth subalgebra A. So it's essentially 4 components. So if we want to have an inductive limit, we have to keep track of all this at all stages. And maybe we can produce a limit of each one of them, but we still have to verify those 2 properties. So maybe some non-canonical formulation of a limit object satisfies properties like this on the limit, but the obvious ones that we will try to write down may not naturally have compact resolvent or this smooth subalgebra. So let me just put it down. So a very general treatment of this question of how to induce spectral triples through inductive limits was studied by Ramesh Florichel and Mergor Mampour. So they studied this the paper is from 2019. So first of all, one has to decide how to produce an inductive limit. So we need maps between the spectral triples. So a morphism between 2 spectral triples, an A1 H1 D1 and H2 H2 D2, with each their own smooth subalgebra, well, will be a pair. It's a phi, a unital star homomorphism from A1 to A2, and an intertwiner I, which is a boundary linear operator from the H1 space to the H2 space. And what should those maps do? Well, the homomorphism should at least preserve the dense smooth subalgebras. So phi of A1 is A2. The representation of A, if we push it with this intertwiner to H2, should just give us the representation of the image of A under the map phi. So this is what pi1 of A is doing. It's the pi2 of the image phi of A pushed with this intertwiner to act on H2. And finally, this intertwiner has to sort of intertwine the domains in the sense that, or rather, it has to carry the domain of the Dirac 1 operator to the domain of D2. And once it does that, we can sort of make this commutation. The intertwiner of D1 is D2 applied to the intertwiner. So this is a natural definition. So you have your spectral triple here, the other one there, and you sort of have to move along both the algebras and the Hilbert spaces and in a compatible manner. So once you have this, you can then think of an inductive system. So an inductive system would be a collection of spectral triples, AJ, HJ, DJ, indexed over an index J, where the maps phi, JK, you have to think that, yeah, so it has to be, so for a deductive system, you would need the J, K, and maybe an L. You need the compatibility of the map from J to L with the composition of the map from J to K to L. So if this is in the inductive system, then we can ask, what can we do with it? Well, so Florichel and Gorbanpour suggested, let's look at the natural realization, which is an inductive realization. You just take the limit of AJs as an algebra, the limit of HJs as Hilbert spaces, the limit of the representations, and the limit of the smooth subalgebras. And you define your D on a psi that is the image in the space coming from intertwiner IJ from psi j in the domain of DJ. Well, you let it act with IJ on the DJ on the Dirac component operator in the jth, where the psi j comes from. So it's sort of defined in the most natural manner that you can conceive. But then, of course, there's no reason why this very nicely, naturally defined triple will satisfy our conditions. So the resolvents need not be compact, and the commutants need not be bounded. All right. So what they proved in their theorem is that they found conditions for resolving both those hurdles. So for an inductive system of spectral triples with the resulting inductive realization just obtained by taking limits in each component, the operator D has compact resolvent if and only if really the sequence is uniformly convergent to the resolvent of D for some lambda. Hence, for every lambda. That's not real. That's purely rational. So if this happens, then D has compact resolvent. The boundedness of the commutator, where the operator comes from the jth algebra in the system, is bounded, again, for some uniform boundedness, if and only if for all indices beyond the j, as you push it to the limit, the commutators of the operator dk with the pi k pushing forward this image here into the kth algebra, if this is a uniformly bounded sequence of norms. All right, so this provides a tool to check whether one has an inductive system of Hilbert of spectral triples behaving like a spectral triple. In our case, and yeah, the examples where I have algebra, so I'll have to resume soon. So in the case of the noncommutative solenoid, we directly constructed the spectral triple on the Sistra algebra seen as a twisted group algebra. So we don't even have the system. So we first have to produce the system, the inductive system, and then we will ask, well, is that realization a spectral triple? Does it satisfy conditions A and B here? And is that what we started out with? So somehow we resolve this, constructing the spectral triple directly on the noncommutative solenoid, restricting it to the rotation algebras in the limit, putting together all the bits into a direct inductive system, and seeing that that's again of the right form. So how do we get an inductive system? Well, fix the prime p, fix the parameter theta. For every n, we restrict to any one of the subgroups where we fix the exponent of the p to be n, and just the restriction of the length function to this 1 over p to the n z. It's still a length function. It has bounded doubling. We produce a representation of the rotation algebra with the parameter corresponding to the even indices 2n on the L2 space of this group gamma n. We realize this rotation algebra as the group algebra of this restricted group 1 over p to the n z times z. So gamma n is this group times direct product with itself. And we realize this twisted group algebra as the Sistra algebra of 1 over p to the n z times 1 over p to the n z with the restricted multiplier from the big noncommutative solenoid to this subgroup. And then we restrict the operator also from the big noncommutative solenoid to this L2 space of this group product with itself. And in this way, produce a spectral triple from the noncommutative torus with the even parameter, theta corresponding to the even index. And the smooth subalgebra is just the continuous functions of the same sort. So there are lots of, there are a couple of identifications of Sistra algebras to keep track of, because from the torus we naturally get this algebra, and we identify it with the noncommutative torus through an isomorphism where we have to keep track of how we move between the parameters. And when we do that, then we can construct a system for those algebras for the tori that on the other direction gives the noncommutative solenoid. So, okay, so the theorem is that for a fixed prime p, and our group gamma, this direct product, and now I call them J, just to go back to the notation of inductive system. So this is the gamma J. We just fix the powers of P to be P to the J. Any parameter theta from this parameter space, if we take the spectral triple that we constructed, the finally summable one, and restrict it to each of the subgroups gamma J with the restriction of the representations and of the Diracs, we obtain an inductive system of noncommutative torus for every J. And when we take the inductive realization of this algebra, of this system in the Flory-Chogarov-Manpour sense, we obtain exactly the spectral triple. And in fact, this direct limit of the spectral triples has the properties of a spectral triple. So it does verify the two conditions. So it has uniform convergence of the resolvents for the purely complex, I think I said purely real, but I mean a purely complex parameter lambda. They converge uniformly. And the family of commutators is uniformly bounded. So the spectral triple on the noncommutative solenoid restricted through the inductive limit of the noncommutative tori produces a system of spectral triples whose inductive realization is again a spectral triple and reconciles the spectral triple on the group C algebra. And I think I have to finish in a moment. I would just very quickly, maybe you already have learned all this from Mark Riffel. I mean, the quantometric structure on a C algebra comes from a seminorm L on a dense star subalgebra on the self-adjoint elements with kernel the real multiples of the identity element. There's a Mons-Kantorovich metric on the state space, which soups the absolute value of the distances of phi and psi on elements A, where this L has value at most 1. And if this metrizes the Wick-Star topology, then we call this a Lip norm, or Riffel calls it a Lip norm. And then the space A with L is a compact quantometric space. And indeed, defining the L of A to be exactly the norm of the commutator of A with the Dirac for the spectral triples we obtained produces, this is my final slide here. There's a further condition of a Leibniz rule on the L. So this inequality of the maximum of L of the sum of AB plus B over 2, AB minus B over 2I should be dominated in this fashion. And we can also obtain that there's a structure as a compact quantum metric space on every noncommutative solenoid where the semi-norm just comes from picking up the norm of the A acting through the regular representation with the DP. And I think this is all I wanted to say. Thank you very much for listening to me.
Thank you very much. Any questions, Adam?
Yes, about this notion of morphism between spectral triples. Does it lead to the category of spectral triples?
So I'm not sure that this has been studied with the full machinery of category theory. It's a working definition. It's a practical formulation of.
So maybe I will be a little bit more concrete. So whether spectral triples with this notion of morphism forms a category.
Yeah, I mean, the question is whether this kind of morphism is really, I mean, composable, right? If
yes,
you impose some conditions, you compose the two maps, and does the composition satisfy the same conditions? That's really the question.
So
But by the way, please note that spectral triples were introduced in 1995. And the first paper which says anything about morphism is 2019. So this was my point. It's like 24 years in between.
yes, so I think, but I think the paper by Fletcher, Gorban, Poor was not the first one. So right now, I would have to look up into that paper to see whether they actually prove that there is a category. I'm not sure. I think there are some positive results about why this definition of morphism is natural, but I do not have the precise details ready now. So mostly at the time, the examples that one was looking at were examples coming from AF algebra. So I think maybe if one looks into the interclass of system algebras, then automatically you would have the properties verified. But in general, I'm not certain that they will be verified immediately.
Okay, and a follow-up question regarding this notion of morphism. Even in the commutative case, when you have smooth manifolds with Dirac operators, even spin, let us say that those manifolds are spin, what would be the right notion of morphism? Which structure do you want to preserve? Everything, or just having a smooth map? Since for commutative spectral triple, there is very rich structure. You have smooth structure, you have metric, but you have also spin structures, and these cohomological arguments about fundamental class. So I wonder which part of the structure you want to preserve, and how this general notion of morphism corresponds to preserving all of the structure.
Well, I think that's a very interesting question. I don't have an answer. I don't know whether these aspects have been studied. There are also, I think, studies of spectral triples for in a more general context of operator spaces. But I think generally those are important questions. I don't think there's a final answer.
Okay, thank you.
So from our perspective, we simply just want to study a very concrete situation. Yes, I hope I have. Yes, I don't know what is the most general result about those spectral triples from the inductive systems. This is what we've been able to use. Yes.
Okay. Any other questions from the room? No. Marius, you're not asking a question. Okay. So anybody from the Zoom, maybe? Okay, I don't see any raised hands. So let me take over. So I have the following questions. First, I'm really puzzled by this dependence or dependence of the prime P. So let's start with a classical solenoid. If I change my prime, do I have homeomorphic spaces or not?
I think there is an entire series of papers by Lachamoulier and Pecker, and I think the reason why they chose the P is probably explained there very well somewhere. So it's the P can just be anything. In a certain sense, you're just you could have chosen just raise any power.
Okay, so these are. So,
I mean, just take any non-zero positive, yeah.
And then the spaces are homeomorphic. Am I right?
Well, I don't know. Piotr, which ones? Where are you?
Well, solenoids. We have solenoids built depending on a prime P. Okay, and imagine that you do exactly the same construction, just change the prime number.
So I assume that you can have.
Because you have some initial point, right? Then you just multiply by P. So of course, I assume that you'd start with the same, say, rational theta, and then keep on multiplying by P and have a sequence. Would it change anything by changing P and keeping, say, the initial theta?
Yes, I don't know about this, Piotr. I would have to look
Okay.
up more carefully some of the constructions from Latremoulier and Packer's papers.
Okay. Okay. Because of course the same question can be now carried over to these non-commutative solenoids, and then to spectral triples, right? Do we have any variation on P? But okay, let's leave it. And
Well,
now
sorry.
have,
So what you say, of course, there are situations where one wants to perturb spectral triples. So I think there's work by Antonescu and Christensen where they produce deformations of spectral triples. I think they through various parameters, and indeed they want to know whether, as you deform your spectral triples, whether what you get ends up being preserved in a manner. So yeah, there are such situations.
Okay, another question
the
is,
other one, of course, will be I mean, but maybe not very varying the parameter, but just taking the limits of the spectral triples in some natural distance. For instance, this Gromov-Hausdorff propinquity, and this has been shown by Fassi, Latremoulier, and Packer, that indeed there is additional convergence if you want, but once you fix your P.
By the way, Adam, you're surprised by this limit. You see, the very motivation for Mark to discover or invent these non-commutative metric spaces, but he was puzzled by a statement by people like John Mador that we have fuzzy spheres, fuzzy quantum spheres, because it's weird that to have a claim that matrix algebras, so they are very non-commutative C-star algebras with the size of a matrix going to infinity, converge to a sphere, commutative sphere. Okay. And they do in the sense of this Gromov-Hausdorff distance.
Yes, and I believe that there is a result. There's also the famous Podler sphere, which is a different story than the fuzzy sphere. But there is also a version of this fuzzy together with Podler, and there is some theorem that everything. I think it goes to Jens Katt probably.
Yeah, I agree.
Well, so the Podler spheres, yes, they have been studied through the perspective of spectral triples by especially by Jens Katt, but also there's some realization of spectral triples for Podler spheres in work of Antonescu and Christensen, where they deform certain spectral triples. So there is work on understanding what the dependence on those spectral triples is when one varies various parameters. But yeah, it's an interesting question. I don't know, Piotr, how all this changes if you change the P's.
Okay.
But I think that there are. So let's see some of the results. I mean, in many cases you get for the aperiodic ones. Yeah, I think you get simple algebras, and there are additional invariants there. Yes. There's a very rich literature really on the non-commutative solenoids. There's several rather lengthy papers by Latremoulier and Packer, so that's probably good reading.
Yeah, of course. Now, how about the K theory? Because the K theory of rational rotation sister algebras, especially looking at the positive cone, is quite interesting. How about solenoids?
Yeah, so is that I think maybe there are elements of it already studied by Latremoulier and Packer. Yeah, I would say that's the place to go. Yes, go and check. There's so much there that has been studied on them. I don't know whether they're complete answers, but
so let me end with a slightly provocative question, if I may. You know the work of Donaldson about exotic smooth structures. So now when we have this complete characterization of say closed Riemannian spin manifolds in terms of commutative spectral triples with some very lengthy list of very particularly fine-tuned axioms, I'm wondering if there's an effect of having exotic structures can be reflected in spectral triples. How is it visible on the operator algebraic level? I know that this is a very vague and provocative question, but any thoughts, any way you would like to weigh in?
I'm not too familiar with the paradigm you're describing, so I would probably just come with a wild guess. But I mean, generally, one would with spectral triples, maybe one would like to maybe see metrics with properties that have not been seen otherwise, or maybe with better types of recognizing certain bounded sets in one place but not the other, or maybe certain types of properties. But
it just occurred to me during your talk, because it's
Yes.
S4, Adam, right? It's S4, yeah. So that fits into the description, and
For
Donaldson
Donaldson, it's
construction is
harmful.
spectacular.
But
so I think what
Donaldson is
we'll
harmful.
probably still want to see is
Euclidean.
more is a larger supply, not just a larger supply of spectral triples, but maybe also a better understanding on how those spectral triples maybe relate to each other, because already just checking all the literature on spectral triples is quite a bit of work. I mean, I've been,
It is
you know,
indeed.
so just trying to put them all into, you know, what are the features from the various constructions, and what's the most general? What should one do spectral triples for Fell bundles algebras, or what's the greatest you know, in a sense, what's the generality of a Sistra algebra construction where you can bring together the various approaches and maybe see something that fits or does not fit? So I would say, yeah, there is, as far as I can see, no sort of just one framework to produce an answer for all the known spectral triple constructions. And whether one such is possible, I don't know.
Okay. Okay, thank you very much.
Okay,
Are we
thank
done,
you.
Adam? Okay, so let us thank Nadia again. Thank you so much.
Thank you for your attention and patience. Thank you for inviting me.
Let me stop recording.
Okay.
We had a very nice floating clapping hands from Marta. Marta, thank you so much.
Okay, thank you. Bye.
I'm really impressed. Can you